In this lesson, I'm going to introduce you to a super important and very useful area of mathematics known as optimization. So to give you a high-level definition, optimization allows us to choose the best version of basically anything we want as we change some of its features. Now, this is a really vague and general definition, so to properly explain it to you, I'm going to introduce three pieces of terminology. Now, first off, we have these things called parameters, and they're just basically numbers that you can change to tweak the object in some way. Now, anytime you perform an optimization, you're going to be interested in your targets, and your targets are basically just numbers that you want to improve as much as possible. And finally, we have our constraints, which are just basically limits on the values that your parameters and targets are allowed to take. Okay, so I'm using words like objects, numbers, and things. Now those are really general words because optimization is a really general technique. It turns out that we can use it to do so many things that you probably can't even imagine them yet. Basically anything in the world that you can write down as a function can probably be optimized in some way. So let me give you some examples to start us off. Okay, so I've started with a picture of an airplane. And airplanes actually have a surprisingly large amount of optimization applied to them. Now there are many things that we could want to optimize on a plane, but let me just give you one example. If we think about the targets first, we would want to maximize the amount of lift and minimize the amount of air resistance that's actually applied to the airplane, because air resistance wastes fuel and lift actually helps keep our plane in the air. If we want to think about the actual parameters that we could change, well, we could change the length of the wing, we could change the shape of the wing, or we could even change the material the wing's made of, for example. But if we want to talk about constraints, there are actually so many that an airplane designer has to consider. For example, they can't just make the width of this wing as wide as they like, because an airplane actually has to fit inside of an airplane hangar. And we can't really choose any shape we want because some shapes will actually cause the plane to become unstable and just fall right out of the air. Now, if you're going to optimize an airplane, even if it's just for two targets like lift and drag, then there are going to be hundreds, potentially thousands of parameters and constraints for you to consider. Or even more than that, but that's what computers are for, right? Now, reasonably, not that many people get to design airplanes for a living, but that is a pretty cool job. But lots of people actually do end up running businesses. And one thing you might want to do as a business owner is to put your business in the best possible place. Okay, so I've just placed your business marker in a random place for now, but let's suppose you did a bit of research and you found out that you had customers all over this map. Now your target could reasonably be to minimize your distance to all of these customers, so you might want to minimize, say, the sum of your distance to all of these different customers. Now in this case, the parameters are actually pretty simple. You just want to find the right latitude and the right longitude to actually place your business. But you better bet that there are lots of constraints too, like you probably don't want to have your business in the middle of this river, and you probably don't want to buy in this suburb because this suburb is really, really expensive. These are all things that you could actually encode mathematically, and you could use something like an optimizer to actually help you solve for the best possible position for your business. Okay, so I'm going to give you just one last example. Have you ever wondered how different websites know which videos to give you to watch next? Well, I can almost guarantee you that there's an optimizer somewhere that's actually figuring out what video to give you next. The target would be to actually maximize the amount of time you spend on this website, or to maximize the likelihood of you clicking one of the videos over here. The parameters would be things like your video watch history, like what have you actually watched in the past? And the constraints would be actual things that stop the recommender from showing you particular videos, like you'd never show this smiley to a kid, would you? So at either rate, these three are wildly different applications, but all of them actually use optimization very, very heavily. Now, this list is not exhaustive. There are so many other things that I could include on this list, and if you just went and talked to basically any working scientist or engineer, I'm sure that they could add thousands more. However, there is a bit of a confession that I need to make. The title here is actually simple optimization, and none of these three cases are actually simple. To be clear though, all three of these have something in common that I should tell you about. They're so wildly complex that humans can't really solve these by hand. In general, we would always employ something like a computer to help us solve any of these problems. However, if we're actually going to show you problems that you can solve by hand, we are limited in the amount of complexity we can actually apply to them. But one thing we can say is that the techniques you're going to learn to solve simple optimization problems will later be generalized to allow you to solve problems even as complex as these. That's usually done in a second or third course on calculus, so it's probably not really that far away for most of you. But just like anything in life, we're going to start simple, and then we're going to get to the more complicated and interesting examples later on in your mathematical career. So without further ado, I think it's time for a new page, and I'm going to actually teach you the techniques required to perform simple optimization. Okay, so I'm going to show you a really powerful technique that helps you visualize exactly what you're doing when you're completing some kind of optimization problem. Okay, so we're going to start by visualizing some kind of mountain range like I've drawn over here. I want you to imagine that these brighter areas are higher, so they're further from the ground. And then that means that these darker areas over here are much closer to the ground. Now for starters, basically any optimization problem that's even the slightest bit interesting is going to have at least two variables. Okay, so these variables are your parameters, and the first step is always going to be to actually identify what your parameters are. Okay, so I haven't told you what we're actually trying to optimize on this mountain here, but I want you to understand that we can control where we are in this direction and where we are in this direction. I'm going to call this direction U, and I'm going to call this direction V. Okay, so once you've actually figured out your parameters, which are all the things that you can change about the particular picture, then the next thing you're going to want to do is to figure out what you're trying to optimize. In this case, I want to find the actual highest point on this mountain range. Okay, so to be clear, there's going to be some function that takes our parameters in as an input and then produces our target as the output. So for example, in the mountain range, we could take the U and V coordinate and then produce the height at that particular position. Now, if you wanted to solve for the absolute highest point on your map, that is something that can be done, but it's not generally something we show you on a first course in calculus. So we are going to need some kind of constraint to actually help us with this problem. Okay, so suppose this path over here represents your constraint. The idea is, rather than talking about finding the highest point on the whole map, we want to find the highest point that we visited as we walked along this path. Now, in a situation where you actually provide a constraint like this one over here, you can't actually choose any value you like. So to actually show you this, I'm going to start by actually converting this map into one of those topographic maps. Okay, then after this, I'm also going to redraw this U number line. Okay, and now I'm actually going to copy a thin section of the path that we walked along onto this axis on the bottom. Okay, so this is probably the most important step to actually solve this problem. Since U is related directly to V by our constraint, then we only really need to know what U is to know how high we were at that point. Or in other words, our target value, or our height, is no longer a function of both U and V. It's only really a function of U, because if we know U, then we can find the height directly. And if we can find the height directly, we can actually graph it directly as a function of U. Okay, and by looking at this cross-section over here, we can now graph the height as a function of U. Okay, so to clarify what we did here, we used the constraint to remove one of the parameters from the target. Now, once you have a function of a single variable, like this, solving for the maximums and the minimums is actually really easy. All we need to do is to solve for the stationary points, and we do that by setting the derivative equal to 0. Now, throughout this topic, we've been dealing with these sorts of functions all the time. And anytime you do get yourself to a function of this form, you can always just solve for the maximums by setting dh on du equal to 0. Now, it's also possible to solve this function to make v the subject as well. But you should always use your discretion to find the easiest possible formula to work with. In either case, however, what you're looking for are these places over here where the gradient equals 0, because one of them has to be the maximum. Now, I've used the word optimal here, however, because you don't just have to solve for the maximums, you can also solve for the minimums as well, if that's what you'd like. In fact, if your particular application requires you to find other things like inflection points, you can find those as well. Now, if you just go and follow these steps, you're going to be able to solve basically any simple optimization problem that we throw at you. But of course, giving you a bunch of steps like this doesn't actually help you solve any of the problems. So what we're going to do is we're going to solve one of these problems. But because this video is getting a bit too long, I'm going to do that in the next part. So join us in the next part if you'd like to see how we can use these steps to actually solve a problem like this one over here.